go to eat. And I've got the kitty.
Okay, back to it. Apparently it's recorded the whole time I was gone. That's okay. Alright. Let's see if we can find another problem here to okay, so accelerating something from rest to a different, to some velocity. Of course, work to be done to accelerate something, you could say it's equal to force times distance cosine theta, except that let's see, yeah, except that you have to know, in this particular case, you have to know the force and the distance. But what if you don't know the force and the distance? What if you just know how fast it's going when it's done? Well, there's this thing that we call the work energy theorem, which said that the work that is done on an object is equal to the change in its kinetic energy. And that's also where we get this whole idea of negative work. If you do negative work on an object, you actually give it a negative change in kinetic energy. You slow it down. If you positive work on an object, you speed it up. Right? So this is what we call the work energy theorem, the beginnings of the work energy theorem. It gets built on more and more and more. But if work equals the change in kinetic energy, and we have a car that we're pushing along in the same direction that it's moving, my cool car, and it starts off at 0 meters per second, and it ends up at 20 meters per second, right? Its change in kinetic energy will be equal to the work. And it's actually, yeah, that's right, I think. Yeah, so change in kinetic energy is equal to the work. So, we'll call this work done on the system. Not by the system. Okay, so anyway, so what we need to do is calculate the kinetic energy. Kinetic energy initial at the beginning is 1/2 m times 0 squared, because that's our velocity. Kinetic energy final is 1/2 mv final squared, which is 20, which is 200 squared. And so then you take the final minus the initial to get the change in kinetic energy, and that will be the same amount of energy that was put into it in the form of work. What happens if you double the speed of the car? How much more energy do you have to put in? What if if you go from 0 to 20 meters per second one time, and the next time you go from 0 to 40 meters per second? How much energy does it take relative from this one relative to this one? How much more energy does it take to double the speed from 0? Remember that work is equal to change in what? Kinetic energy, which is equal to 1/2 mv squared. So if you double this thing, what happens when you double something and you square it? Double means you 2 times it. What if you square 2 times? It becomes 4 times, right? So instead of taking twice as much energy to make something go twice as fast, it takes 4 times as much energy to make something go twice as fast as the last time you did. So, right? And this goes back to that idea we talked about with our friend Émilie du Châtelet, the French woman. Because one of the experiments that she explained was this experiment where they were dropping things into a tub of clay. So here's the tub of clay. And they would drop things such that the speed would be, let's say when it hit the tub of clay, it was going 3 meters per second. And this thing would come down and hit the clay, and it would sink into the clay some depth, d. And then they would drop it from a higher height so that it would hit the clay going 6 meters per second. And what they found was that it wouldn't go twice as deep, it would go 4 times as deep when it was going twice as fast. Because it took 4 times as much energy to stop it when it was going twice as fast. And this is what really has people who understand physics, who understand who have been around accidents, scared. That's what makes people scared when they see a speed limit in Wyoming that says like 85 miles an hour. Because 85 miles an hour is not twice as energetic as 45 or 42.5 miles an hour. It's 4 times as energetic, which means it can do 4 times as much damage as a 45 mile an hour accident. A 45 mile an hour accident is more than enough to kill a human being. 25 miles an hour is enough to kill a human being without an airbag. Especially if you hit another car coming straight at you at 25 miles an hour, because then your combined velocity or your combined overall speed relative to each other is twice that. It's 50. And so, as you raise the speed limits on highways, you're not increasing the danger by however much you increase the speed. You're endangering it by however much you increase the speed squared. Right? And so it just makes no sense to increase the speed on highways. I mean, we should lower them down, in my opinion, back down to 60 or 65. Because going at 75, 80, 85 miles an hour, our cars are not good enough to handle that. If you wreck on the freeway going those speeds, you will die. If you're going 80 miles an hour, guaranteed death. I've never met anybody who's survived a car crash over 75 miles an hour. I don't think there is anybody that has. Anyway, so it's the speed squared. The energy is the thing that causes the damage. Yeah. Oh man, they took out my favorite problem. This problem used to name a specific pitcher, which is one of my favorite pitchers, Tim Lincecum. They talk about pitchers who throw over 100 miles an hour, and the old one that they did had it said that Tim Lincecum recently pitched one of the fastest pitches in baseball at 102.7 miles per hour or something like that, which was really amazing considering he's such a wimpy little skinny guy. Anyway, 100 miles an hour, right? Local team is drafting up and coming left-handed pitcher who can consistently throw at 91.5 miles an hour, assuming the ball has a mass of 0.1438 kilograms, speed just before a batter would make contact. How much kinetic energy does the ball have? So they give it to you in meters per second, which is 40.9. They give you the mass of the ball in kilograms, so all you have to do is plug it in. Kinetic energy of the ball is 1/2 times the mass of the ball times the velocity squared. Right? Just before the batter makes contact. How high would the ball need to be dropped from to attain the same energy? Well, this goes to our potential energy problem, right? Kinetic energy is 1/2 mv squared, to get the first part out of that. But potential energy, which is the amount of energy that you could have if you were dropped from a certain height and you fell all the way through it, would be m times g times h. So in this problem, you're going to set these two things equal to each other. You're going to calculate 1/2 mv squared and let it equal the mgh, and you're going to calculate the h. You can see here that the mass doesn't matter; it cancels out in this case, and the h ends up being equal to v squared over 2g. So the V in this case is about 40. Square that, you're going to get 1600. Divided by G, you're going to get, by 2G, you're going to get about 80. So you have to drop it from 80 feet. You have to drop it from nearly like a 7-story building, the top of a 7-story building, to get it going as fast as Tim Lincecum can pitch it. Actually a 10-story building, because he can pitch a lot faster. Well, he used to. I don't know if he still can. Nobody knows if he still can. He's not playing baseball. What's wrong with that guy? Let's see. Okay, the next problem is a bit of a conservation of energy problem, or we'll call it a transfer of energy problem. The next problem, we have this guy Harold the Hurler. He's throwing a baseball, and he's at the bottom of a pit. That's what we do in physics. We go to the bottom of a pit. It's actually, he's just doing his homework, and he feels like he's at the bottom of a pit. So, here's the bottom of his pit, bottom of his homework pit, and he throws this ball upward, right? And this is where you're going to find out that that energy is much better than forces. He's going to throw this ball so that it smoothly lands in the third floor window of a nearby building. It smoothly enters the tube of this machine he calls the baseball absorber. So it goes into this tube smoothly without losing any energy. And then it hits a spring, so there's a spring in this tube, and it compresses the spring, and it comes to rest momentarily until the spring pushes back out again. The compression in the spring is recorded to be 0.405 meters, and it has so that's the delta X of the spring compression. And the spring has a spring constant of 847 newtons per meter. The position of the baseball's momentary rest is 7.25 meters above ground level. So this distance right here is 7.25 meters. And then the distance from the ground to the pit, the bottom of the pit, is 14.5 meters. We don't know how much work Harold does to perform this feat. How much work does Harold have to do? Well, it comes down to some pretty simple stuff, actually. It's not as hard as it looks, in other words. The first thing we have to do is we have to decide, where is our 0 point going to be? Where is our zero energy going to be? And I usually pick the lowest point in the problem to be my 0 point. You don't have to. You can pick ground level if you want. But I'm going to pick this point to be my 0. And I'm going to say that the potential energy at this point equals 0, and that everything above that is positive. Positive. You have to choose where your potential energy is going to equal 0, because potential energy can be negative. So I'm going to just pick the lowest point in the problem to be potential energy equals 0, and everything above that will be just cake. Well, in order for him to throw it up to this point, he has to essentially give the ball all this potential energy. And as you give the ball all this potential energy, it's going to change. Where is it going to come from? Where's that potential energy going to come from? After the ball leaves Harold's arm, so here it is in the air, and he's just thrown it, it's just left his hand, what kind of energy does the ball have? As it's just left his hand, how much energy, what kind of energy does the ball have? And we're assuming he throws it from the ground. He actually throws it from 14.5 meters deep. So, what's that? So it only has kinetic energy here. It doesn't have any potential energy because this is a, so kinetic energy equals something, some number, but potential energy equals what? At the bottom of the pit? 0, right? And the spring up at the top also has energy, but before the ball hits it, it has no energy stored in it. So the potential energy of the spring initially is 0, and the kinetic energy initially is some number, and the potential energy initially is 0. Right? And then, when it gets all the way to the top and it's just going in the window, what kind of energy does it have? Well, you've raised it up a bunch of distance, so what has it got? It's got some potential energy at the top, and then we'll call that potential energy final, some number. What other kind of energy does it have? Because we know it's still moving. So it also has some kinetic energy final, right? But it also presses in the spring. So that's just at the top. We'll call this at the top, not final. We'll call this top. So we'll give it a capital T. But the final potential energy, or the final of everything, is it has potential energy when it's finally compressed the spring. It's still at the top. So it has some final potential energy. But once you've compressed the spring and it's come to a stop, the kinetic energy actually equals 0 at the very end. And then the potential energy in the spring has some energy in it, right? So I'm just kind of mapping it out. I'm going to go to my next page and I'm going to go through each stage of this without the picture. So just after the throw, we said it has kinetic energy. We'll call that kinetic energy initial. And then we said potential energy initial equals 0. And we said the potential energy of the spring initial equals 0. Okay. Because the spring hasn't been compressed or anything yet. And then we'll say after compression, after it's compressed the spring. As long as we haven't lost any energy in friction or other things, which we're going to assume we don't lose much, so it doesn't matter that much. But after we've compressed the spring, the kinetic energy, final, is 0 because it comes to a stop. The potential energy, final, is some number. We want to figure that out. And the potential energy of the spring has some number involved with it, right? So we know that it has potential energy, final, potential energy from gravity, and potential energy from the spring at the end, but no kinetic energy. Well, in reality, conservation energy is going to tell us that if we add up all these types of energies at the beginning and add them all up at the end, they should equal the same amount of energy as long as we haven't lost them in between. So that's what we're going to do here. And this is a conservation of energy problem. That's how you do this. You set up an equation that looks just like this. Kinetic energy initial, which is something we don't know because we're going to find out how fast he's throwing at this point. That's the thing we're going to find out. I'll put a question mark about that. Plus potential energy initial, which is 0, plus potential energy of the spring, which is 0. So those are just 0 plus 0, equals kinetic energy final, which is 0. Potential energy final, which is going to be m times g times h, which we can calculate, right? And then the potential energy in the spring, final, which is also a number we can calculate because it's going to be 1/2 times k times x squared. So we can calculate everything on the right, and then we can get what is on the left. And from that, from the kinetic energy initial, we can calculate what the initial velocity is, which is what he wants to know. He wants to know how fast the ball is moving. So we have to plug in 1/2 mv squared over here, initial. And we're going to solve this equation for velocity initial. The rest of these problems are essentially variations on this problem. Sometimes they'll add in some work and some other things, but they're variations on this kind of problem. Remember that any force can do work, any force can add or subtract energy from a system. Friction usually subtracts energy for the system. So if you're going to do that, if you're going to have friction in your system, Make sure that it's written into the equation in such a way that it takes energy away from things. But energy problems usually end up having a bunch of energies at the beginning added together, a bunch of energies at the end added together, and set them equal to each other and solve for the things you want to know. So go ahead and get started on that. Finish up the last homework. Get started on this one. Make sure that you email me with your questions. I will be available by email, and I can make videos for that as well. And I think we're going to be done for now. There's a lot more problems in here, but they're all kind of just they're all just variations on the themes that we've done so far. So just practicing with energy. So, any questions before we break today? You good to go, Keegan? Okay, don't forget to email me if you have questions on the homework. And we will see you next week. Now, next week is July 4th. Technically, we're not supposed to meet that day. I think we probably should, just because we're going to be short on days here, meeting left. Anyway, are you available to meet, Keegan, or are you going to be busy for the 4th of July? Okay, check to make sure that you'll be available if you are going to be available, or if you're not. Either way, send me an email as soon as you can so we can know what to do. I will go ahead and have some kind of a lecture that day regardless of whether or not you're going to be able to meet. And we will, and I'll put that on YouTube, and so you can watch it and get going on things. But let's get this week out of the way, and next week we'll start some new assignments, and we'll see you guys then.